Hello, I am Bill Doran, and this is my Lab 5 lab report video presentation. To give an introduction to this lab, the purpose of this lab is to collect observational data of a magnet falling through an aluminum foil tube. That's like the actual experiment part. I did that in real life, and then to compare this data with computational predictions from a model of the magnet and tube interaction in GlowScript by using Faraday's law, which describes the electric field and induced voltage created by a changing magnetic field. It is possible to relate this time-varying magnetic field to a Curly electric field. And in the model, that means finding current in each ring of the model's representation of the aluminum foil tube. Materials for this experiment included my smartphone, the tube of aluminum foil, a bar magnet, and in addition to Faraday's law, other relevant physics principles for this lab include Phys law to measure the force on each non-interacting conductive ring that makes up the tube, especially when modeling, and also Newton's second law to iteratively update velocity and position values, which is really important when we get to the model. And my findings from Lab 5 were that the aluminum foil tube slows the rate at which the magnet falls, and this did line up with the data that was produced from my model. So in terms of procedure of the experimental portion, first I had to use my smartphone magnometer to find the north pole of the bar magnet and mark it, and then record the time it takes for the magnet to fall through the tube by filming the experiment with my smartphone. I repeated that 5 times, and then also recorded the time it takes for the magnet to fall the distance of the tube, but on its own. This wasn't specifically requested, but it was interesting, and I wanted to include this in my lab procedure. So the average time to the floor in the tube was just over 1 second, and the average time to the floor with no tube was around 1/4 of a second. So as you can see, it's a pretty drastic effect that the presence of the metal tube has on the time it takes for the magnet to fall. So here is some significant portions of my code. First, just plugging in values from my experiment that were necessary for the model to line up to the experiment and give results similar to the experiment. In addition to a function that created the calculations for the magnetic field of the bar magnet, as you can see right here at the bottom of the screen. Continuing on, I made a function for the magnetic flux, and then edited different values for the force, in addition to the net force on the magnet, and then as I mentioned earlier, these 2 lines down here in step 8 iteratively updated the velocity and position, and then it was plotted in this model, which didn't line up exactly with my collected data, but it did show that the relationship is about the same. So wrapping up with questions, what if the resistivity of the conductor were reduced as close as possible to 0? The magnet would fall slower because of the increase in magnetic force caused by an increase in the induced current that is applied on the magnet. And then what if holes or slots were cut into the tube? How would this affect the ring currents in your model? So it's kind of the exact opposite. The resistivity would be increased, actually, and the magnet would fall faster because the magnetic force would be decreased, and the induced current that is applied on the magnet would decrease as well. So that was my Lab 5 presentation. thank you very much for watching.